Again. And what we're going to do in the second part of the lecture today is give you a simple example of payback time. And the example we're going to take is with different light bulbs. So here's a fairly simple question. If I'm going to put some light bulbs in the room that I'm in at the moment, which of these technologies do you think might be the cheapest? Well, that's a difficult question to answer directly without giving any information. And it's difficult until I give you some capital costs for actually buying the light bulbs. Now, if I do that, in the days that you could buy the 100-watt incandescent light bulb, they were pretty cheap and typically about 50 pence. If I wanted a 70-watt halogen lamp, that would be about £3. And if I wanted a 20-watt fluorescent tube light, that would be about £10. And the point about this is most people will go for the item that has the lowest capital cost. But when I said about costs, there are multiple parts to the costs here. So capital cost is one. If all you want to do is minimize the capital cost, you'll buy the 100-watt incandescent light bulb. But when we start to also think about how long these light bulbs will last, for instance, here the fluorescent bulb that I put in has about 8,000 hours lifetime. And each of them is going to consume a particular amount of electricity. So you can now start to see that if we look at the costs over 8,000 hours, we put in a particular price for the electricity we're going to use, it's not completely obvious which one is going to be cheapest until you start to do a bit of a back of the envelope calculation. So let's do that. And we've got the three columns for the three different technologies. So let's look at the amount of energy or the amount of electricity that each of these technologies will consume over 8,000 hours. Well, this is fairly easy. We multiply the number of watts that we've got by the number of hours, and we'll get kilowatt hours. So the 100-watt incandescent light bulb, it's 100 times 8,000, so it's 800 kilowatt hours. When we look at our halogen bulb, well, it's 70-watt halogen bulb. We multiply that by 8,000 hours, we get 560 kilowatt hours. And for the 20-watt fluorescent, well, it's 20 times 8,000, and it's 160 kilowatt hours. So you can see already that there's about a factor of 6 difference between the 100-watt incandescent and the 20-watt fluorescent over how much electricity we're going to have to use. So if we work out the electricity for that, well, it's 13 pence per kilowatt hour. We just multiply by the kilowatt hours for each. And for the incandescent light bulb, we get 104. For the 70-watt halogen, we get £72.80. And for the 20-watt fluorescent, we get £20.80. So you can now start to see that, in fact, when we look at light bulbs, it's not the capital cost of the light bulb that dominates the price in this system. It's actually the cost of the electricity to run it will actually dominate when you take a very long-term view of the technology and the real costs. But also what we haven't spoken about is that each of these technologies has a different lifetime. So the incandescent light bulb typically will only survive 1,000 hours, and then it breaks and you have to buy another one and replace what's there. So while we said it was 50 pence capital costs, over our 8,000 hours, we're going to have to buy 8 of these, and that's £4. Now, we can argue whether it's 7 or it's 8, depending on exactly where it breaks in this, but let's use 8. If we do the same for the halogen, we need 4 of them over the 8,000 hours. And for the 20-watt fluorescent, we're just using 1 over the same period. So you can see now that actually the capital costs have changed. You might have thought that the halogen was cheaper than the fluorescent, but over the lifetimes, actually, the halogen is the most expensive in terms of capital costs, simply because of the lifetime of the light bulbs. Now, if we put these all together over our 8,000 hours, we add the electricity plus the capital costs. You can now see that the incandescent light bulb is actually the most expensive of the technologies. So the fluorescent bulb, when we include the electrical costs and the capital costs, is the cheapest technology. And the longer we run the period of time for this calculation, the cheaper it becomes. So you can see in this that, in fact, the European legislation that dictated and actually banned incandescent light bulbs. We showed in the first lecture how we can substantially reduce the number of power stations that are required. That means we reduce the carbon emissions for lighting in the UK. But also you can see here, in doing that, we're actually making it cheaper overall for consumers to light their homes. Now the payback time. Well, the compact fluorescent lamp has the highest initial capital investment, but it's got the lowest fuel costs. And if you plot over a period of time, over the number of hours of use, you can see the step change that goes on, and that's your capital cost when you've got to buy a new light bulb. So for the incandescent light bulb, it's quite a small change because it's 50 pence. The £4 in our halogen lamp is a bit of a bigger jump. And this, you can see the capital cost gives the initial jump at 0 hours of use. So you can see already that we only have to go to about 1,200 hours before the compact fluorescent lamp is cheaper than the other technologies. So in this particular example, the payback time is the time of the additional capital investment and is therefore only 1,200 hours. Now, when we talk about borrowing money, the payback time is similar, where we pay back the capital investment. And so, with this example, if we had to borrow the money to buy the light bulbs, the payback time would be 1,200 hours as well. Now, this is a very simple example. It's relatively cheap capital. Most people can go out and afford even the £10 compact fluorescent and pay for that. When we start to talk about power stations, and you might be talking about hundreds of millions of pounds, and with nuclear, that gets well into billions of pounds. There is no way even many multinational companies can afford to put that amount of money into a project. So you borrow money from banks and you have to pay back. And that's what we'll go on to and start to look at now. So typically a company will actually be involved in running a power station. So generally with companies, we've got income and we've got expenditure. So even where it's a nationalized company, still typically in countries where you have nationalized industries, there will be a company set up so that you can understand the income and the expenditure in a particular sector or for a particular energy. So incomes, well, things like sales, so selling the energy, you'll have cash in hand. Expenditure, well, materials, labor, maintenance, rent, that could be fuel, particularly when we're talking about fossil fuel power stations. Investment, well, leasing capital. It may be a case that rather than building a power station, you might actually just lease a power station from another company. But if you build it, you'll need the purchasing capital, and that's an expenditure. Financing cash flow. Well, if you're going to purchase capital and it's a large power station, you'll probably need the income of loans from a bank to be able to actually pay for that. The other way in the markets you can pay for that is what's known as equity, either the internal money in the company or financial investors put money into the company with the expectation of making a profit over a period of time. And of course, the loans that you take from a bank, you'll have to repay those over time. There will be taxes if the company makes a profit. And also, if it's a private company, you may also pay dividends off the profit levels to your investors that have put equity into the company. So you can see here that equity is really the thing that allows the company to function, but there's an expectation that the private investors putting equity in will get dividends and make a profit over a period of time. Now, the other thing that is quite important in all this is that a company needs sufficient cash in hand to be able to trade and operate. So it needs enough income, and that income has to be greater than the expenditure to allow it to function. Now, there's a time frame between income coming in and the ability to pay it out. And to make sure that a company can still function, it has to have a particular amount of cash in hand or cash available that it can pay its bills with. And this is where you see differences between companies going into Chapter 11 and going into full bankruptcy. That will depend on how much cash in hand. So Chapter 11 is typically where there's insufficient cash in hand, but it's still a viable business to function. So let's start to compare a few power stations. Now, the trouble with looking at costs and prices is that they change every year because of inflation. A few other things we'll talk about later in this lecture that are absolutely key. So I'm always going to normalize to a particular time when I talk about costs and prices. So for this lecture course, I wrote it about 10 years ago. All the prices are normalized to prices as they were in 2010. What you have to do to work out what that price would be in present money is go through the inflation on different years, and from that you can work out how much more that would be in 2021. But if we look at a nuclear power station, and this is Sizewell C, and the original look at it, the power rating was, it was 2 nuclear reactors with a total power rating of 2.6 gigawatts. The capital cost in 2010 to build it was £5 billion. And it was proposed to have a 40-year operating lifetime that it would be generating electricity. Now we can look at gas turbines. Here's a combined capture gas turbine plant. It's 400 megawatts, so it's much smaller than the nuclear power station in terms of the electricity it can generate. It has a capital cost of 320 million, so it's a much lower capital cost, but it can only operate for 20 years before the turbines and the boilers are worn out and it gets shut down. And as a final example here, here's a 1 megawatt wind turbine from Siemens. In 2010 prices, that was £1.5 million to buy. And it was rated at a lifetime before it's likely to fail of 25 years. So here's a couple of questions. So what's the total cost per kilowatt hour from each of these power stations for the electricity? And also, what's the capital costs per kilowatt hour of the electricity? So this is important if you're going to make an investment in any of these power stations, and to understand how much money you have to borrow from a bank and whether you're going to make a profit, but also at what price do you have to sell the electricity to the consumer to make, well, first to pay back the investment that you have to borrow, but then also to make a profit. So does anybody want to guess which of these 3 technologies is the cheapest? So this is a question I ask the students every year. And typically, I always have a few guess, but the majority of the students really are struggling with the numbers in front to understand which one is the cheapest. And you'll see as we go through and actually cost this out, it's a difficult problem to guess which one is correct unless you've been through all the calculations in detail. We're going to do these calculations a little bit piecemeal, and you'll understand why when we get towards the end. But there's a lot of different costs come into this, and not just the costs that I've shown here. So if we look at the total costs of a hypothetical power plant, we've got to break those costs into different constituent elements and typically calculate the costs of each. Now, as an example here, if we look at wind turbines, we don't have any fuel for a wind turbine. So depending on which technology we're looking at, a fuel may be important if it's nuclear or it's fossil fuel based, but it may not be important if it's a renewable technology and won't be part of that. So while this is general, please be aware that some of these sections that are in here are not appropriate for every single generation technology. Another example is that there may be environmental costs, and this comes down to carbon pricing or carbon taxes. That will be, again, dependent on which country you're in and which carbon costs are used in that country. And it also, again, is heavily dependent on which technology you're using. And there may also be subsidies. So there may be money that comes in to actually reduce the costs in some countries as well. So just to say that some of these elements are unique to a particular type of energy, so carbon taxes, environmental costs, and decommissioning, well, actually decommissioning is a cost over every single power station that we're looking at. Typically though, it's only talked about for nuclear because the decommissioning costs of nuclear are significantly higher than the decommissioning costs of any other energy generation technology. But every single power station has a decommissioning cost. And a good example in the UK is, over the last 3 or 4 years, a number of the coal-fired power stations have been decommissioned and have been shut down. And if you look on the news, the BBC News and on YouTube, you can see a lot of the explosions that happened for actually taking those coal-fired power stations and going back to brownfield or greenfield sites. So, just to say, in some of these you'll see capital costs can be the largest, and certainly for nuclear, it has a very high initial cost. So we have to think about annuitizing the costs. So what do I mean by annuitized? Well, we spoke about light bulbs. Light bulbs are quite cheap. The capital investment is not large. Almost anybody can afford to buy even the most expensive light bulb. They may choose to buy the cheapest capital cost one, but at least for the price we're talking about, anybody can buy the most expensive light bulb technology. For power stations, particularly for nuclear or for gas and many other forms, the capital investment is enormous, particularly if you have to pay and make a single payment before you build anything. Now, in reality, companies don't make a single capital payment for any technology. They will make a payment over a number of years. They'll typically borrow money over a number of years. So what annuitized is really talking about is the cost per annum. So to find comparative costs, it's the annuitized cost, which is spreading the cost over a number of years, is actually used. So we're breaking the cost of a power station that may have 40 years generating lifetime, and we're looking at the cost per year, and we'll have to borrow money, particularly at the start. So let's do some simple examples to illustrate what I'm talking about here. It's far easier to show examples so you can understand what annuitized costs mean. So let's take the combined cycle gas turbine power station that was 400 megawatts in terms of the base plate capacity. The capital costs McDonald proposed for that power station were £800 per kilowatt. It had a design lifetime of 20 years. And typically, it would run for 7,500 hours per annum with 50% efficiency. So we'll talk a little bit later today about the capacity factors for different power stations and different technologies and what they are. To do this, you have to make an assumption over what the capacity factor is going to be. Some of that will be historical. If you have a new technology, that's more difficult. But as you'll see, capacity factor can really change what the cost and how much money you have to borrow ends up being. So we're going to buy gas at a wholesale value of 2 pence per kilowatt hour. And the maintenance costs are 0.6 pence per kilowatt hour. So this is all data for a real power station that was built in 2010 in the UK by the civil engineering company Mott MacDonald. So the prices for gas have certainly gone up. Maintenance costs have certainly gone up. But this at least gives you a good example of how you find the cost of the energy per kilowatt hour. So it runs for 7,500 hours per annum. So the first thing we have to do is work out how much electricity we've produced in kilowatt hours, so we can then work out the cost of that electricity per kilowatt hour. So the maximum, or the base plate capacity as it's called, was 400 megawatts, and it ran for 7,500 hours in the year. So if we multiply this up, if we change this into kilowatts, it's going to be 400,000 kilowatts times 7,500 hours. We end up with 3 billion kilowatt hours, or 3 million megawatt hours. The total capital costs, well, for this particular power station, it was £800 per kilowatt. In terms of kilowatts, it's 400 megawatts, so that's 400,000. So the capital cost we have is £320 million. So for this particular power station, I expect none of the students in this course, unless their parents are extremely rich, would be able to go into their pockets and pay £320 million to build the power station. So this is going to be something that even many multinational companies will borrow money from a bank and pay it back in monthly or in annual installments. So the annuitized capital costs, assuming we're just doing a straight division over the number of years of operation, is to take the capital costs and divide by the number of years of operation. So that's a £320 million divided by 20 years. And so it's £16 million a year. Now, it's much easier to pay £16 million a year than £320 million up front for a power station. And the other reason this works very well for businesses is because if you pay it back after the first year of generating electricity, you've sold the electricity to customers who have paid the price, and you've got money back that allows you to then put it straight back in to pay the loan to the bank. Now, you'll see a little bit later in this lecture, this is not the right amount of money to pay back. And we'll talk about the time value of money and interest rates and so on. But if we this is a very simple, if we assume that there's no inflation, there's no time value of money, then it would be £16 million we would pay back each year to pay the bank the capital costs of building the power station. So the annualized capital cost per kilowatt hour of electricity produced, well, that's going to be our 16 million we just calculated, divided by our 3 billion kilowatt hours, so the amount of electricity produced. And that gives us 0.53 pence per kilowatt hour. Well, that's just the capital costs. So you can see already that per kilowatt hour, well, this looks pretty cheap compared to the, well, at the moment, typical electricity in the UK is about 15 pence per kilowatt hour. In 2010, it was about 13 pence per kilowatt hour was the price to a consumer if you were buying electricity for a house or a flat. So you can see now the capital cost here is tiny compared to the cost of the electricity sold to a consumer? Well, part of this reason, at least with gas, is because we haven't paid for the fuel yet, and we also haven't paid for maintenance. So the gas cost we said per kilowatt hour was 2 pence per kilowatt hour. Now, it's not as simple as that. This power station has an efficiency of 50%. So we have to take that into account. So we actually have to burn 2 kilowatt hours of gas to be able to get 1 kilowatt hour of electricity, because the power station is 50% efficiency. Now you'll see when you look at different textbooks, you can put the efficiency in different parts of the calculation, but it has to go in somewhere. So when you solve these problems, you need to put it in somewhere, and there may be different parts of the problem you can put it into. But here I'm doing it in terms of the fuel, that we have to basically have twice the amount of fuel of the output we're going to produce, because the power station runs at 50% capacity. Sorry, it runs at 50% efficiency. Now, operation and maintenance was 0.6 pence per kilowatt hour of electricity produced. So the total cost per kilowatt hour for this gas-fired power station is 5.13 pence per kilowatt hour. So you can see for the gas-fired power station, the total cost is 5.13 pence per kilowatt hour. The capital is relatively low. The operation and maintenance is relatively low, but the fuel costs dominate the cost of the electricity. Now, when we look at other technologies, these will change. So for instance, when we look at wind turbines, there's no fuel. So clearly the fuel costs are zero, and something else will dominate the cost of that electricity. But for gas, it's the fuel costs that dominate. Now, this is a very simple way just to illustrate what you have to do to get the cost of electricity. We'll go through now and we'll talk about the time value of money. Because when you borrow money from a bank, you don't pay back the amount you borrowed. You pay back a higher sum. Now, part of that is for the bank to make a profit, because it wants to make a profit, but also money changes value over a period of time. And I'll illustrate that now. So when you look at economics and how the costs, whether it's of energy or of anything else, are calculated, there's what's known as the time value of money. And the key thing to understand about this is that if you spend the money now, then it's not in a bank making interest. So one of the things this is all about is it better to make an investment? Is it better to leave your money in the bank and get the inflation over a period of time? Or is it better to go and do something else where you'll get a better return for your money? But money, if you just leave it under your pillow at home or somewhere in the house, actually loses value over time. And that's what I'll explain in this. So we had an annualized cost of 5.13 pence per kilowatt hour. That excludes inflation, the time preference for money, and the opportunity costs. So the opportunity costs are really this: consider the money left under your bed or under your pillow, compared to the interest you would earn if you had that money in the bank. But in economics, it's a key concept, and it relates scarcity and choice. So you don't have an infinite amount of money that you can do every single opportunity that's open to you. So you have to make a choice how you spend the money you have. And opportunity cost is about how you use that money with scarce resources and use it efficiently. So the time value of money. Inflation erodes the capacity for money to purchase goods over time. So I showed you the inflation values in the UK earlier on, and they've been running for about the last decade at roughly 2%. So if I had £1 in 2010, I can't buy something that cost £1 in 2010 now, because actually it's cost more because it's gone up by 2% every year. So the time preference of money looks at, most people might want £1 in their pocket today rather than in the future. So interest is paid as if money is loaned to another party. And if you return it in 1 year time, you'll pay X% extra because the value of that money can buy less in 1 year's time. Also, with the interest rate for a bank, you'll have some profit level that's put on top so that the bank can make a profit as well. And overall, that's the complete interest rate. So I should point out here that the time preference for money still exists even if inflation is zero. So the point about this is there will always be other opportunities you could go to, and banks will always pay you some interest rate because they can put that money into different investments. They could build a power station, they could build a different factory, they could put it in a different investment and make a profit. So the point about the time preference of money, even if inflation is 0%, is people can still make a profit by investing that money somewhere else. The opportunity cost is the cost if money is spent now rather than investing, or if the money is lost in a poor investment that fails. Now, I know for a lot of students, what's on this slide is quite difficult concepts if you've never seen them before. They're very simple accountancy principles. They're basically how banks work and how you calculate the cost of anything if you borrow money and you have to pay that money back. So if any of you have mortgages for flats or for houses, or if you have one in the future, this is exactly what you go through over to work out the interest rate for the bank and how much money you'll pay back each year for the money you borrowed to buy that flat or house. So let's give some examples. So let's assume that the interest rate was 10%. Now, I know in the UK it hasn't been for quite a while, but 10% makes the numbers easy, and it really shows a good example of the difference that you get. Let's say we have £100 today to pay a bill, and if the bill is in the future, then actually if we put that money in a bank and we get interest of 10%, we can pay bills that are more than £100 in the future. Well, how much more? Well, if it's 10% per year, so in 1 year, I'm going to get 10% interest, so I'll have £110 in the bank in 1 year. So I can pay a bill in 1 year's time of £110. Now we can do the same for 2 years. Well, it's a compound here, so it's actually our £110 times the 1.1, so it ends up being £121 in 2 years. If I do 5 years, well, in fact, we just take the exponent 5 into this equation, and we can start to look at this at n years, but you can see after 5 years, I've now got an additional £61 above the £100 I started with. If I get 10% interest every year, I leave the money in the bank. If I do it for 10 years, you can start to see this builds up, £260. So the future value of £100 in 10 years' time at 10% interest rate is £260. Now, if I don't put the money in the bank, actually, I've lost money. So if I leave my £100 in my house and don't do anything with it, after 10 years' time, it's lost value. So in fact, if we turn the numbers around, actually, if I've got £260 in my pocket today, and I don't do anything with it over 10 years, if the interest rate is 10%, it has a value of £100 in 10 years' time. And this is simply because I'm not doing something that I'm getting interest or I'm making a profit or getting a return on investment. So this is a key economic principle and how you end up setting interest rates. And so you always end up losing money unless you're putting money into investments. So discounting is what this is called. And it's basically that any sum of money I have today is worth less in the future. So I have to take this into account when I'm costing my power station. So if I'm going to borrow a particular amount to pay the capital to build the power station today, I also have to pay back the loss of the value of that capital because of discounting over the period of time I will pay back the money to the bank. And this is why interest rates that you have, even when inflation is 0%, are still always positive and finite and greater than zero. So discounted, it's compared to the sums of the money I have today. So discounting is this key concept that the money is worth less in the future because you're not getting interest if it's not in a bank. So when you borrow money, it will always be discounted and you will pay back additional because of the discount rate plus the interest rates. So sorry, the discounting is a key part of how the interest rate is calculated. So I should say here, discounting and interest are not the same. So the real interest rate is the monetary interest rate or the base rate of the country minus the rate of inflation. And discounting is really about due to uncertainty. People would actually prefer the money in their pocket today rather than having it and not spending it and having it around tomorrow or in a time in the future. So the discounting is money today can be invested for more than the money that you have tomorrow. And inflation describes how the price rise of everything with time erodes the real value of money. Discounting is much more to do of the lack of interest that you get by not having the money in a bank. And I should say that many texts wrongly interchange discounting and inflation. So the discount rate always has to be greater than the interest rate. And that's something that is a technicality in economics. But again, some accountancy books interchange these terms and don't define them exactly. Right, so I'm going to give you now two different formulae that are absolutely key to being able to cost the price of electricity when you borrow money. So the discount accounting formula. So we have the present value VP here, and we have a value Vn in n number of years. We have the discount rate, so that's how much we lose over a number of years, and we can work out what the present value is with this formula where we've got the value in n years and then 1 plus the discount rate to the power n. So this is really taking the £100 and multiplying it by the interest over n number of years. And if you do that, you basically get this formula here. So the present value for one sum of money in n years, for a sequence of sum of monies over n years, this gets summed up. So this is the value in one particular year, in the year n. But actually, if we're borrowing money or looking at it over a number of years, we have to sum it over all n years, and we get the net present value. So the net present value, we do this for year 1, 2, 3, up to year n. And when we sum this, we end up with V for the year I, 1 plus an I summed up to the year n. Now, actually, it's this slide that's the most important. And this is the slide that you will understand if you have a mortgage and you understand how you calculate your interest for a mortgage. This really is the basis of that, but using it with discounting. So in annuitization, if all the repayments on a loan are equal and a value A is the annuity, This is what you pay back every year in the money that you've been borrowed from the bank. So the present value of the annuity A is VP here. So VP is the total amount of money that you've borrowed. That's the amount of money you need to build the power station, or the amount of money you borrow to buy the house. The annuity is how much you're going to pay back each year. And it ends up being the sum of 1 over 1 plus the discount rate to the power 1 for year 1, 1 over 1 plus the discount rate to the power 2 for year 2, up to 1 over 1 plus the discount rate to the power n for the nth year you're going to borrow the money for. Now, if we take this and turn it around to have the annuity out the front, this tells us how much money we have to pay back each year to the bank, the sum A, for a total amount of money VP that we've borrowed. And if the discount rate is R, then it's the total amount borrowed times R divided by 1 minus 1 plus R to the power minus n number of years we've borrowed the money for. Now, when we do this for a whole power station, we have to look at the payback time and the time it generates electricity. And that will help define what n is in this equation. If it's a house, then we're borrowing VP from the bank now, and the sum A must be paid back every year for n number of years. So with mortgages you take out, you can decide with the bank over how many years you want to pay it back. Typically, because interest is added on top, interest is part of the discount rate in here. So this has got the time, so the discount rate has the time value of money plus any profit that a bank will have involved in it. And with this, it allows you to calculate the true value or the true cost of energy because of the money you have to borrow to build the power station. And it will give you a good idea over at a particular price you can sell the energy at, what the payback time will be. Okay, so this has all been quite theoretical about the economics and the basic accountancy. We'll now go through some examples, and it's far easier for all students when you see the examples and how this is used. So typically, if you go in to see a mortgage company or a bank to get a mortgage, what they'll do is they'll give you a table like this, that if you borrow a certain amount of money, then over the number of years and at different interest or discount rates, depending on how much the interest rate you pay changes, it allows you to work out how much you're going to pay back each year. So this is basically for values per £1,000 that you borrow. So for example, if I borrow £1,000 at 0 discount rate, over 10 years, I'm going to pay back £100 each year for 10 years. So, I would love it if I only had to pay back the £1,000 completely and there was no discount and interest rate. But if there's a discount rate of 2%, then I would have to pay back £111 over the 10 years. So in fact, I'm paying £110 more than if I wasn't paying the discount rate. We can look at many other examples here for power stations. It might be 20, 25, 30, 40 years. It's much more appropriate. Discount rates are much more likely to be 5 to 8%. At the moment, the UK recommends about 5%. So you can see over 40 years, at 5% discount rate, you'd be paying back 58. And you can work out how much more than 1,000 that actually is. But it's more than twice £1,000 that you're paying back over the 40 years. So let's go back to our combined cycle gas turbine power station. So without discounting, without any interest, without the time value of money, the total cost per kilowatt hour of electricity was 5.13 pence per kilowatt hour. But we would have had to have borrowed the £320 million to be able to build the power station before we can sell any electricity and get the money and pay back the money. Annuitized value of £1,000 over 20 years, let's say it's at 10% discounting, would be £117 per annum we would pay back. So let's say we're now borrowing this money. We're going to have 10% discounting. That makes the numbers nice and easy to calculate in your head. We borrowed £320 million to build the power station. If we're going to pay it back at 10% discounting, then we're paying back for every £1,000, £117 per annum. Well, that's 320,000 times 117. We're actually paying back £37.44 million a year. Now, if you remember, before we had interest and discounting in this, we were paying back £16 million a year. So you can see already that the amount of capital in this cost has already doubled simply by putting in discounting. So you can now see that discounting is quite a key parameter to get right. And it's very important when you're costing power stations and costing energy, because it can make a significant difference to the cost of energy and therefore the price you can sell it at to get payback and make a profit. So our annuitized capital cost per kilowatt hour of electricity, well, it's not 16 million divided by 3 billion kilowatt hours anymore. It's now 37.44 million divided by 3 billion kilowatt hours. So rather than 0.5 pence per kilowatt hour, it's now 1.25 pence per kilowatt hour. So it's gone up by 150%. The fuel costs are still the same. Now, fuel prices will change over time, but typically we don't put discounting into fuel costs. We may put an inflation value in if we want to look at the real costs over the complete project. And operations and maintenance, again, we don't put the discounting in, but we may have to think about how that changes with inflation over time. So you can see here, now we put everything back together, the price per kilowatt hour has gone up from 5.13 pence per kilowatt hour to 5.85 pence per kilowatt hour because we've had to borrow the money to build the power station. So this is a good time to take a break. I will stop the recording